Hi, in this exercise we are going to see how to model this 2D steel plate with a crack, central crack, standing from one edge to the center of the crack. The plate has a base of 50 mm and a height of 70 and a thickness of 2 mm. And it is subjected to an external uniform tensile stress of 500 megapascal. So to start with the modeling, we are going to first generate the part. The part should be 2D planar, shell, deformable, and so we can generate the external geometry of the part, 50 by 70, okay? And here is our plate. So now we need to generate the crack, and for generating the crack, what we are going to do is create a partition using a sketch. Okay, so we will generate this crack from the edge to the center. In addition to this crack, we are going to generate two circular areas around the crack tip for better controlling the mesh and the accuracy of the calculation. So we are going to generate these two circular areas. The first one with a diameter of 5 and the second with 12. So now we have this part with these two circular areas within. Now that we have the part, we can go for property, generate the material. This material should be steel, okay, should be mechanical, elasticity, elastic, it's isotropic material, and then the Young modulus is 210,000 megapascal and 0.3 for Poisson. So now that we have the material, we define the section, should be homogeneous, steel, plane stress, and a thickness of 2 mm. And now we can apply this section or assign this section to the plate. So it's section 1, we didn't rename it, material steel, and from section. So this is it. Now that we have the section, we can generate the assembly, the instance based on the part, and we will make it independent. So mesh will be on instance. Now that we have defined assembly, we can go for defining boundary conditions, and we are going to define first in this initial step the boundary conditions based on displacement rotation, because what we want is apply the external pressure on these horizontal edges and restrain the displacement of the part in this central point of this lateral edge. So doing so, we see that we can select the edge but not the central point. So to define or to have the option to define the boundary conditions in this central point, first, what we are going to do is generate a partition, but a partition based on a midpoint of the edge. So we will select the edge, this is the edge, and now this midpoint. So we create the partition, and now we have this point where we can apply these boundary conditions. For displacement rotation, we select now this point. Okay, so we restrict the horizontal and the vertical displacement. So this is okay for the boundary conditions. Now we need to apply load. And load, we need to generate first a new step. Okay, this new step will be based on initial, so the same boundary conditions will be transferred, static and general. Okay, time period, we are going to set this time period equal to 20. Okay? And we are going to activate the nonlinear geometrical effects. Also, in the incrementation, we are going to set this initial increment size to 0.01, and the maximum increment we will force it to be as 1. Okay, so with these conditions for the step, now we can go for loading. We can generate this load. It will be mechanical, and instead of concentrated force or moment, we are going to select pressure. We will select the top and bottom edges of the part, and here is where we are going to apply our pressure. That should be minus 500 megapascal, minus because we want it to be tensile, as we see the arrows pointing outside. Okay, so once we have the load already defined, what we are going to define is an interaction, and in this interaction is where we are going to define the conditions for the crack. So we will go for a special crack. We will first assign sim, and we will assign sim to these edges defining the crack. Okay, once we have this, we will go back to special crack, and we will create a crack. And this crack will be based on contour integral. We need to select the crack front area, will be the inner circular area we define, and also the crack tip, which will be this point here. Now we need to assign the crack extension direction. That could be done with normal to crack plane, but in this case we are going to use the cube vector. So we are going to define 2 points, initial point and final point, defining the direction of the crack progression. So here is where we have the conditions for the crack. General is okay, but for singularity we are going to force the mid-side node parameter to be closer to the crack tip, so 0.3, and also collapse element side single node for the generated element control at the crack. Okay, so with this we see that the elements tend to concentrate the nodes around the crack tip. Once we have this, we are going to generate a new history output. Okay, and in this history output, instead of selecting the whole model, we are going to select crack. Okay, J integral, but the number of contours we are going it to be equal to 4. So with this we have everything ready except for the mesh. So now is when we go for mesh, and before starting meshing we are going to assign controls. Okay, so we are going to select these 2 regions. Okay, and in these 2 regions we want to have quad elements, free and medial axis. In the inner circular region or area, we want to have triangles and use mapped meshing and also free. Okay. Once we have this, we want to also control the type of element. So again, we will select these 2 areas here, and in this case we are going to select the standard, but quadratic, plane stress, which the program already selects for us, but we don't want reduced integration, but full integration, so it's CPS 8. Okay, there is a warning, but this is because we haven't changed the element type in the inner circular area yet. So let's do that now. So standard, quadratic, plane stress, triangular, but we don't want modified formulation, so CPS 6. Okay, so now we can mesh. We can set the size of the mesh. We will use an approximate global size of 2 millimeters. Okay, but now we are going to modify, because we want here only one element in this edge direction. So instead of keeping these divisions in this edge, we are going to modify it, and instead of having a dimension of the element by size, we are going to force it to be by number, and we only want one division. So now we can mesh. Yes, mesh the part, and here we obtain this regular and relatively nice mesh for this problem. Now we have everything ready, so we can go for job. We can create a job based on model 1. Okay, we can submit. Yes, and it should be relatively fast to have the results. So the model has been submitted for calculation. The first step the checking is complete successfully, and in a moment we should have, here it is, completed. So now we can check for the results. So the first thing we can do is see the deformed shape. We see how the crack opens. It's open but not that much. We can exaggerate the opening. So instead of auto-compute, we can force it to be uniform and a value of 5. Okay, so this is how it deforms, and here is where we see the von Mises stresses. We see that the von Mises stress is relatively high, or it's too high, 11,300 megapascal, but this is basically concentrated at the crack tip. And we see that the stress, the level of stress decreases rapidly from the crack tip. So in this area, this level of stress is less than 900 megapascal. So we can go back. We can also see what happens with the reaction forces. We see that the reaction forces is completely concentrated in the node where we apply the boundary conditions, or we can see for displacement. Okay, even we can ask for an animation, how this plate deforms when we apply this external pressure. Okay. And also we can see that in this case, that I stopped the animation, we finished, or we ended in increment 13 and step time 2.5. So this means that we are not at the end, but we can move or go fast to the final step. So in this case, increment 31 and step time 20. So this is it. So this is how we calculated this steel planar plate with this crack.